So it's now my pleasure to introduce Katina Michael, also from ASU, but ASU in Australia. So she's up early in the morning, about 3:30 a.m. over there, and she's going to give a really interesting talk on TinyML technologies and neuromorphic computing. So with that, I will hand it over to you, Katina. Thank you. We can see your slides.
Thank you so much, Steve. Sorry to stand everyone up a moment ago. Welcome to my talk on tiny machine learning and neuromorphic computing, an area quite close to my heart, particularly because I've been studying the onset of implantables, both in biotechnology and also for commercialization. So let's begin with traditional information processing. You've got an input, you manipulate the information, and then you get an output. But in the meantime, you try to store that data somehow as it's being processed. Information in, information out, and hopefully it's not garbage in and garbage out. Increasingly, what we've seen is this landscape of edge devices interacting with the nodes in the edge, and then with the core being the cloud environment. And what we have is these hops going from the access point, which is the edge device, into the edge node and into the cloud for storage of this data. So there's processing on the actual device on the edge, there's processing on the node, and there's processing again in the cloud. And what we're trying to achieve is not only to gobble more and more data in order to garner big data, to analyze it and gain some intelligence, but we're also attempting to store as much as we can to become more visible in our actions and behaviors. So by collecting data, we can use that to train systems through machine learning, and we can also use it for intelligence purposes, feeding back into processes and cycles. But the human brain doesn't really work by having disparate sections on a CPU. It's much more fluid. And you can see this amazing network of networks before you, these neurons, and the synapses that are forming between them. There's massive parallelism going on here. There are less steps. There are faster ways to find patterns than actually going to the CPU, going to the storage, going here, going there, and wasting all this amazing time. And so the brain works analog, it works asynchronously, and it can separate out noise to detect patterns better than any machine out there. These are the neurons. If we focus and zoom in, and the connections between the neurons, as I said, are called synapses. We try to sort of be inspired by this union, these electronic signals being sent in the brain. And the brain has more than 100 billion neurons that communicate in trillions of connections. And the payload for what it's doing is quite small, relatively speaking. And so what we've attempted to do here in this story anyway is to create neural networks using software. And we can see here on the right the attempt at the parallelism through software and modeling the brain and the nervous system. And so that's been a good start, but we are still limited by this von Neumann sort of architecture, this traditional CMOS and classic architecture, which decompartmentalizes the memory away from the processing, very different to the human brain. And so there's a lot of time wasting, there's a lot of latency between all of these hops in the CPU itself, and there's a lot of consequent energy that's required to power the CPU. Think now millions of CPUs in order to somehow get closer to how the brain actually functions. And the data stores required to run these programs are huge. They're costing us an exorbitant amount of money. In fact, many people have predicted if we keep going this way by 2050, we won't have enough energy supply to cover what's required out there if we go on the current pattern and approach. I want you to think about this a bit like the pharmaceutical industry, which has really hit a bit of a intersection here, or a roadblock really. It's a T intersection that says we can go no further with our discoveries really. What we can encourage is for people to take their antibiotics more behaviorally sensitive, and so they're taking them on time every day without forgetting them in an optimal way. But we really can't do better than we've already done. We've really discovered everything there is to discover, from penicillin onwards, even those drugs that look at things like antidepressant and antisuppressants and so forth. And so while Big Pharma has abandoned antibiotics, the question is whether the big tech corporations will abandon the current style of CPUs in favor of neuromorphic computing, in favor of quantum computing and other kinds of available approaches in the selection environment. And so there is this push for new materials in the hope that we would garner some better benefit there. The design of new hardware, as we've seen with this rise of neuromorphic computing. Intel's talking about it, that they're still in research mode according to their website. ARM, BrainChip Inc. and all of these other organizations out there. Of course, Google riding on the tail of this with their TensorFlow, Light products and other open source software, and new software constantly coming out, new tools, and the biggest thing I believe is the new programming abstractions. Good luck to our programmers to actually come up with those. And we did try for a little while, and still are, doing a hop from the CPUs to the GPUs, the graphics processing units, because they sort of have a lot more firepower as we've used them for multimedia, animation, gaming, 3D, what you name it, in order to visualize things, in order to do things that are more complicated, like look at satellite photography and imagery, but also do these amazing installations, as we've seen NVIDIA come out with. But even they have their limits. The problem with a lot of these devices is if we start to stack them too much and we deploy them simultaneously, literally the chips will begin to melt. And so we're stuck here with physics, really. We've faced, as I said, the end of the antibiotic era, but for potentially CPUs. And it's not like CPUs are going to go away. They will have their function. But the question is, what are we going to do when we need greater computing? And we begin to look at different ways of scaling. Here is an example of the Human Brain Project and Neuromorphic Computing, a paper back in 2013, which said we've got to look at the whole aspect of this. We've got to go towards this, looking at how we can correlate back to the human brain that only requires some 10 to 20 watts to make certain actions happen. For example, playing a board of game of chess. And we compare that to the firepower of our computing, which needs 1,000,000 watts at times, depending on what is going on. And so here is a fundamental architecture of neuromorphic computing, where we see this correlation of memristas storing information as it's learning by doing and by being, if I can put it that way. Not being as in human being, but actually interacting, learning by doing. And so the synapses are being carried there with the ions, and what we are trying to do is to replicate the human brain. What we are trying to forgo is that we have low computing power requirements. We get rid of this latency issue because the memory is co-located with the actual processing power, the neuron itself, and we have millions, hopefully, of these neurons on these neuromorphic chips. So can we get further into what we had hoped with mimicking and being bio-inspired? Now, the reason why we're going down this path is the reality is if we were making more money still with CPUs, we would probably not care. We'd still slog it out with more CPUs. But the real dilemma here is that it's costing us more to produce these chips that have more transistors on them. And so Moore's law has almost collapsed around 2017, and now our phones, our laptops, our IoT devices are costing us more. So when companies like Intel and other organizations, are not speaking on their behalf, attempt to squeeze out a bit more on that chip, it's costing them more to develop, and it's costing us as consumers more to consume. And so what do? We have to look elsewhere. And here was that infamous DeepMind Google game of Go, where, of course, the human lost 4 out of the 5 games. Of course, the computer used the 1,000,000 watts, the human the 20 watts, and it was a brute force kind of approach, although they did say that DeepMind was using some level of intuition after it had been thrown so many different variables of matches in the past for it to learn from, watching other people's games. And so one commentator from Stanford said, this is as close as we're going to have a computer come to intuition. We thought it would take 10 years to get to this point, but it's happened a lot sooner. And so when I say brute force, I'll just caveat that it wasn't brute force as in a traditional kind of engineering brute force, but it was here's the training data, learn it, modify it, use your abilities to respond to moves as the human player was making. And so a movement away from this front end of client infrastructure, which requires the internet, so sort of your edge devices on this point, requires the internet again to hop perhaps between 5 and 7 hops, depending on the originating point and the destination point, or terminating point I should say, and then all of this stuff here in the cloud, at the back end. And so what are we doing? We're going to replace this. We're going to bring devices closest to us. We're going to bring the machine learning closer to us. We're going to put the machine learning on that edge device. So my camera, for example, rather than spitting it out to the cloud and waiting for some kind of gesture response and camera correction, may well do it on board. And we're already seeing these things even with Samsung phones, for example, doing some of the analysis on the handset rather than going back. So we are looking at different kinds of applications that are being pushed closer and closer to that last mile, and if I could say, the lowest common denominator, the embedded system itself, whether that system is on the human being, being lugged by the human being, or on a lamppost, or some kind of medical device, it's embedded, if we want to use that term loosely. And so think of IoT devices that don't require to go back or have an internet connection to do, for example, a translation, to do a lookup in a dictionary, to wait for a wake word, for example, or some kind of word that is key. And so this is the energy we're saving by going on to these hops, and also the latency that's being overcome as these devices get closer and closer to us. And so here are 3 examples, a tiny machine learning devices, the Pico 4ML, the Arduino, which I want to come back to, the Bluetooth enabled sense, and the STM microelectronic sensor tile. And I show these for a couple of different reasons. These are the kinds of chips we're talking about where the TinyML we're actually residing. And so looking at the cloud, looking at the mobile, and looking at TinyML, and then comparing the architectures, the memory requirements, the storage and power, you can see how much TinyML does make sense for certain applications. We're going from a cloud-hungry 16 gigabyte NVIDIA Volta GPU to perhaps a 256 kilobyte SRAM MCU ARM device, which will possibly do a similar function, if not the same, without the requirement to be so hungry for energy. And so applications can be divided into vision, voice, and vibration. Let's call these the new 3 V's, as we did in the supply chain with other 5 V's, but it's all about capturing insights from intelligent cameras through object detection, human pose estimation and gait perhaps. Depth estimation is a big thing, especially with augmented reality. Voice, we're looking at keyword spotting, automatic speech recognition, translation, beam forming, going directly to a RF signal, for example, and noise suppression, and a whole bunch of other things on vibration, such as human activity recognition, detection, sensors, and so much more. So I could ponder on this slide for literally half a day, but I'm going to move on in the consciousness of time and just say that different types of applications require different kinds of wattage, from the microwatts to the milliwatts. And so we're hopeful that we could simulate a diseased brain and progression of a disease such as dementia or Alzheimer's, and we can do that, for example, through brain on a bench kind of technology. We can see how this evolves over time, and some people may well prosper from this kind of research by slowing down things or by moving faster towards deep brain stimulation devices that could be sitting on the actual deep brain stimulation device closer to the action, monitoring what's going on, preventing, for example, in the case of epilepsy, if it's a vagus nerve stimulation device, some kind of seizure, and then responding quicker without the need to go remotely or even to back up stuff on the cloud later on. So these feedback mechanisms could be incredibly important in medical applications in the future. And so again, layers, a process of design where you build a model, You train the model, of course, you evaluate, optimize, convert the model, deploy the model, and then make inferences. I want to finish with a couple of slides here, looking at different kinds of kits. Again, I did identify the Arduino Nano before, and just say have a look at the kinds of sensors that are packed onto this Arduino device, and using TensorFlow Lite again to do different kinds of system sketches to see the potential of what a learning kit could do, for example, at a university. But these are the kinds of things that the greater the number of sensors, the greater the kinds of things we can do with these. Spotted this one about 5 years ago. Autodesk researcher had an implantable device that had a vibration motor on it. This is way before TinyML, so we could see that people were experimenting with potentially in-body devices that could have operational scenarios with on-body and even external devices like lampposts, and looking at the different kinds of things that could happen in terms of that, whether it's a medical response or it's a support for someone who's disabled or has a function missing in terms of prosthesis, or perhaps a way of the future of how we're going to communicate. We see again these kinds of stylistic sketches, and finally some real applications here. The Vivo Key application, which was launched about 3 or 4 years ago. My dear friend Amal Grafstra, who actually implanted an Arduino device in his forearm, he's tethering his mobile device, an external device, with the Arduino in his forearm. And what can that give birth to? Imagine TinyML in that kind of context. And then we have the most recent project I'm a ethical, legal and social implications panelist on for DARPA, which is looking at the ability to slow down jet lag, to recover from jet lag for the US warfighter, and also to overcome traveler's diarrhea. These are all applications that may well be going and using TinyML. My final slide here, we're going from billions to trillions of devices potentially if this goes forward. Low power requirements, that's great for the environment, but depending on how many of these there are floating around, I wonder. Batteries the size of coins, lasting weeks, months, some people even say, depending on the configuration and information management, years. The machine learning happens at the edge, reducing latency. Who bears the brunt of computation on the device itself rather than the cloud, and the ability to sense patterns and bidirectional feedback. That's all I have to say. I'm sorry I've gone a couple of minutes over, but I hope you found that entertaining, and it's more an exploration rather than a deep dive into any particular technology, but a movement away from cloud computing perhaps to tiny machine learning. Thank you.
Wow, that was certainly a whirlwind tour of neuromorphic computing, Katina. Thank you. That was, like you said at the beginning, very holistic view of what's happening and where it's going and where TinyML fits in. I don't see any questions in the Q&A sidebar, but to all attendees, please ask away, and we'll get you answers from Katina. And with that, I guess we should move on just to keep on schedule. We do have